So yeah, as Jan mentioned, I'm going to talk about what we did on Lucene. First off, introduce a little bit what the context of it, and even what's Lucene for those who are not familiar with it. So it's an index search engine. So an index search is something that lets you find in a text database documents that corresponds to like a phrase that you specified. I mean, it's a Google search, it's something like that, with a Wikipedia search, whatever. The way it's built is that first you build an inverted index. An inverted index is something like, if you ever read, I don't know, some of you are very young, but if you ever read a paper encyclopedia, right? There was one book at the beginning with an index, so you've got every important word and in which page that word was accessible. So that's what an inverted index is. That's what lets you do quick searches. So Lucene is like it's a very popular library for index search. And in the past, we had done already sort of a small use case, UPIS, for UPMEM index search, that did pretty good in terms of performance, but it was really, a bit of a toy. So, when it comes to Lucene for DPU, so the project here was to make a sort of extension of Lucene that would, use the real Lucene, work within it, and just allow us to offload certain queries to UPMEM PIM, but not necessarily all of them. That way you can have a fully working Lucene in production with some UPMEM acceleration. So we wanted to have a non-intrusive extension. We want to have some options on when we want to use PIM or not. We want more throughput, less energy consumption. We don't want to negatively impact the performance of regular Lucene. And so the idea is going query by query and implementing that. And the one we're interested in is phrase query, which is simply, you provide a phrase like, it's just a sequence of words like blue tree, and you want to find all the documents that contain the phrase blue tree. So we decided we don't want to change the existing Lucene index. Just in parallel of it, we create an index for PIM, that's supplementary. We've got this Java class PIM index writer, which lets us create the PIM index for Lucene. So the process is, okay, you create a Lucene index, then you read it, create the PIM index from it, you synthesize it, and each DPU is assigned a subset of the documents, and it contains the entire index for this subset of document, and that's how you spread it. So, I mean, you've got an example. Let's say for a term here, you have your index, and then it's gonna be assigned. Segments of it are gonna be assigned to each DPU, depending on the document index. Though something that's different from the UPIS project, the PIM index are sorted in a different order because this is more efficient once you want to do stuff like fuzzy queries and prefix search. There are 4 parts to a PIM index. First, the field table, is just when you consider text like Wikipedia, there's a body field, a title field, references, and so on. So it just, most of the time, of course, we're interested in body. And then there's like a hierarchical separation. There's 2 degrees of pointers that lets you quickly find where to look for the term that you want to reach. So first there's the block tables, and this is like a sort of a table of content, right? That's going to tell you, okay, quickly, here is a general region where you want to search for your term. And then there's a block list in each of those regions, which is terms one after the other, and so you scan linearly through it to find the term you're looking for. And this is a small example if you had only 6 terms in your index. So the main loop, right, when you're searching for document indexes on the DPU is the following, right? Basically, it's done in 2 steps. You look at each document, and first you do a document selection. That means in this you say, is it possible that this document contains the phrase I'm looking for? And for that, it needs to contain every single word of your phrase. Otherwise, if you don't have blue and tree in a document, you can't have the phrase blue tree. And then if the document is selected, if it's valid, then you look for all the occurrences of blue and tree in the document, and you try to find if 2 of them are consecutive, and if that's the case, yeah. So typically, this you do document selection a lot more often. You do it for every document, but it's very fast. And the word alignment is the costly part, usually. And this is what results in sort of load balancing issues, and we'll come to that later. But okay, so you loop over every document ID, and you do all that process, and then at the end you have a list of documents, with valid hits. So the way it works, the way it's used, in fact, you create a query class in Lucene that extends the regular query classes for PIM. Then the system will decide whether or not to run it on PIM, based on rules, or whether or not you have PIM on your machine or not. And then there's like one global manager that will collect queries coming from different threads. So you can run several searches in parallel. It's just going to use the same PIM system. And then it's sending all those queries as batches to the DPUs. And then at the end, there's a score calculation to be done for each document. It's kind of a complex calculation that comes from Lucene. There's a lot of arithmetics, nonlinear functions in it. So we do the actual score computation on the host. And here's an example of how you create the PIM index from an existing Lucene index that you've already generated. And here's an example of how you generate a search. Basically, you have to create an index reader. Then you have to build a query, and then which you then submit to the searcher, and you get your results. It's not very important. All right. So in Lucene, there is this concept of segment, and the way it's done is that it takes quite a long time to generate a Lucene index, especially if you have a big database of documents. And so the idea is that Lucene can be updated incrementally. So if it's Wikipedia, like every night or every week, they generate a new segment which contains a new document that have been added to Wikipedia recently, and it is added onto the existing Lucene index without modifying what's already here. So that way, there's a little work to do every time. You can even do that for every document. So yeah, this whole index is immutable. I mean, segments are immutable. You can delete document, but the segment will still be in there. It's just marked as deleted. And the idea is that once in a while, once every month or so, you just regenerate your entire index. You just consolidate everything together and sort of restart from a clean state. But it's important, for the use of Lucene to support this whole segment incremental update. So how do we do that on DPU? Okay, the idea was it was going to be a bit hard to have segments for the PIM index. So in fact, we don't do it. We just pretend to do it in a way. We have to generate an entire PIM index for every Lucene index iteration, but then we just sort of present the API to Lucene as if we had segments. Yeah. And then, but mostly, that's the trick here. So that was one of the optimization. You know, after we added the scatter gather transfers to the DPU, you know, rather than just collecting the data from all the DPUs to the host and then doing a bunch of mem copy to reorder everything, we just use the scatter gather transfers to put together results that belong in the same query and in the same, at least that belong in contiguous queries and segments. And that saves quite a lot of memory shuffling. So another thing is you know, load balancing, right? So how do you separate the work? So maybe naive way, or one of the first ideas that will come to mind is to say, okay, we're going to parallelize over queries, so each DPU is going to receive a different query. In practice, this is very bad. I mean, if we use like the Lucene benchmarks, because some queries are very simple, some queries are very complex, some queries have a lot of hits, some queries have no results. So if you do that, you just have terrible load balancing. You're just waiting for one DPU to finish. It's a very long task. That's why it's a better idea to divide the entire index by document ID and just divide that to all the DPUs. So that way, all the DPUs are processing the same queries, but over different documents. So what did we get in terms of results? You know, let me show you first the machine that we used for that. You know, it's one of our cloud machines. I believe it was PIM Cloud 10. Yeah, before. Sorry, it's an internal one, sorry, my bad. Yeah, so we did that test with the Wikipedia dataset, just the entirety of English Wikipedia. And then we use a bunch of queries that we send all at once that come from the Lucene nightly benchmarks to test the performance of the system. So if we look at the DPU profiling, you know, it looks pretty good. There's not a lot of white space. There's a bit of, you know, that's what happens when you do a bunch of stuff in parallel. Okay, there's always going to be a tail like that. But other than that, you know, it looks good, and it's kind of it's a fake impression. It's actually not very good at all. What's happening is that all the ranks are doing the same amount of work, more or less. But if you look at individual DPUs, if you time their execution, you realize that the load balancing is terrible. And for every rank, you're just waiting for one DPU to finish its works every time. It just, you know, on average, that results in similar rank duration, but not a good overall load balancing. So what do we get in terms of, you know, actual acceleration? So this is the acceleration of you know, the PIM system versus CPU only, with a different number of search threads, sorry, by color. And so, okay, what's this n-top docs here? Basically, when you do a search in a Lucene or, you know, any index searcher, you're telling your searcher which result do you want. Do you want to find all the results, all the documents that match, or do you want to only find the best 10 documents? Which is, you know, typically the case when you're doing a Google search, where you only want to see the first page. The thing is, okay, the CPU version of Lucene, you know, the CPU implementation, is very good at using a low number of top docs. Because the way it works is it keeps in mind the best scores that it has already found. And so there's a aggressive pruning happening. Like if you're looking for only the best 10 results, and your worst, you already have 10 results with a score of over, I don't know, 50, whatever, and then you look at a new document and you see that there's only a maximum possible score of 20, well, you're not even going to look at the document. You know, you can just ignore it. And so the DPU the CPU implementation is very good at that because you've got all these threads that communicate pretty fast between themselves on an x86, right? And they can share together this data structure of what are the current best results. And on DPU, well, we don't do that. Like we're sort of far away from the host CPU. It takes quite a bit of time to synchronize. And that's why, yeah, on low number of top docs, we're doing, in some cases, worse than the CPU implementation. Whereas if we want all results, well, in that case, we are doing quite a bit better. Okay, one thing to note, there are 2 levels of parallelism possible in Lucene. One is, you can execute your search of threads in parallel, but you can also have different queries. I mean, I guess the point of that graph is to show that if you try to use both levels of parallelism at once, well, then it's a bit counterproductive because then you've got some a lot of thread preemption issues and rescheduling and so on, and this kind of costs. Right. So this is something similar to 2 slides ago, right? It's just to say that compare PIM Lucene to standard Lucene, and we see that, yeah, the CPU Lucene can really take advantage of a low number of top docs, and PIM Lucene really cannot. So when we were at this point, the next step was to say, okay, this is where we really need the direct WRAM access, because all this is a synchronization issue, and if instead of doing this thing, well, we stop, we synchronize, we stop, we synchronize, and every time we stop, you have to wait for the slower DPUs, and synchronization itself is not free; it's still quite a lot of time. Instead of doing that, if we can just have the DPUs running the whole time, and then communicate via WRAM. What's the current maximum? So they can prune the documents, and they can also send their results, their temporary results, what's the current best, and so on and so forth. And so we did that. I mean, it's just one slide, but this is what took the most development time, right? We use the parallel WRAM access for that. The host maintains a heap of the best results for every query, but it shares, with all the DPUs. And in the end, yeah, even with low number of top docs, we get an acceleration. Still not as good as what we get for a large number of top docs, but it's something. So was it worth it? I don't know for Lucene specifically, but mostly, yeah, this has been a really good proof of concept for the WRAM parallel access. Showing that it works. It can really be used to accelerate this kind of applications. And hopefully, if you want to see the WRAM direct access in action, or other than in the documentation, you can look at the Lucene project to have full scale pictures of its use. Let's say. Thank you very much.